Hello everyone, welcome to my talk. My name is Naci Şimşek. I am Customer Success Manager at Ververica. And today's talk, I will be focusing on the Flink mistake playbook, three Flink issues I see commonly for our clients, customers' Flink use cases. And then I will be going through their root causes and then possible fixes. So let's get started. So here is a little bit background of me. I have been working in different organizations, including Huawei, Telefonica, and then last 2 years at Ververica. And then the last 10 years, I will be working on the data domain, having different kinds of roles, including data engineering, BI, data warehouse engineering, platform maintenance engineering. And then the last 2 years, customer success manager at Ververica. We are supporting our clients in their Apache Flink and then also the Ververica product use cases. So let's start our presentation. So in this presentation, I will be going through these three main issues. So I will be discussing their root causes and then the possible fixes. So the first one is migrating Flink from the old to the new Kafka connector, which is being done commonly with our Flink users. The second one is distributing the load evenly among task slots. When increasing the parallelism, having a parallelism in our Flink jobs, it is really crucial for us to distribute the load evenly in these task slots. And then the third one is avoiding the performance issues of the Kryo fallback that we are commonly seeing in the client's use cases, and then it's just reducing the throughput and increasing the latency. So I will be just touching the details of that one and how to avoid the Kryo fallback. So the structure of the presentation for each issue will be again the symptom, and I will be describing the issue and then the root cause of that issue, and finally I will be explaining the solution and then our recommendation. So let's begin. So the first issue is, migrating the Flink from old to new Kafka connector. Our old Kafka connector is Flink Kafka Consumer, and then the new one is the Kafka source, of course. So our clients are mostly moving their use cases from old Flink Kafka Consumer to the new API Kafka source. This new API is giving us some capabilities, including dynamic partition discovery, build and checkpointing, exactly one semantics, and then of course it has fluent builder, cleaning config. It is for sure having much more ability than the old consumer, and it's been there for a while for the new API. So, and then the Flink document is suggesting users to that the old Kafka consumer is already deprecated. So users are moving their workloads of the Flink to the new Kafka source API, and then the new source API is already been there for quite some time. And then even the document is just indicating that the old Kafka consumer API is deprecated by Flink 117. It's still there. Even Flink 118, it should still be there. So still many users are still migrating their jobs from old to new API. And then the symptom of our users mostly seeing is that when they restore their Flink jobs, they are facing an exception. Either their Flink job is failing with the RPC invocation size, that size is exceeding the maximum akka frame size, or they are facing in their job managers is out of memory. Why this RPC invocation size exceed is happening, which is over their maximum akka frame size? The thing is, when the job is restoring itself from a save point, this save point file is being fetched from by the job manager from the object store, and then job manager, by using this underscore metadata file, it's fetching the operator state and then distributing that operator state to the task managers by using this RPC call. And then since this underscore metadata file size is too big, so the operator size is big, the size of the data that job manager tried to pass from itself to the task manager is going bigger and bigger. So that metadata file size cannot be fit in this RPC call request. That's why the akka frame size issue is happening. So why this underscore metadata size is getting bigger, which is causing this issue? Actually, this underscore metadata file is an inline save point file. Normally, save point file can consist of underscore metadata files and plus some bunch of other files which can consist of some keyed state. But when the file is with some Flink settings, can be inlined and all the states can be into this underscore metadata file, it is basically consisting of, again, the operator state and then the keyed state. By operator state, we mean that it's just keeping your Kafka topic partition offsets. And then the keyed state, your operators can have list, map, or value states that you just calculate based on a key. It will be consisting of all that state data. So how that state looks, it is looking like this. So the operator state is consisting of your Kafka topics that you are reading from, and then it has partitions. Right now in this example, I'm just having 10 Kafka partitions, so each partition ID has its offset values here listed. And then the keyed state is you are keying your data like key by based on, let's say, a device ID. You can see the aggregated values for like counts and sums, which is consisting your keyed state. So what we are focusing in this talk is our operator state is getting a high volume. That's just causing the inline metadata file is getting too big. So the thing is, when we're just focusing on our operator state, we are of course having our old operator state, which is from like the Flink Kafka consumer operator state, which has an object of topic partition offset state objects. And then the new Kafka source API is the name is Kafka source, and then it has list state descriptor object. So the object name is source reader state. So the object type, these Kafka consumer APIs are different from the old consumer to the new consumer. And then you can see the comparison between the old deprecated consumer and then the new Kafka source API. So their state structures, state names, partition tracking types, all these entities are just compared in this table. But right now for our talk, what we are focusing on is the state name. You can see that the objects of the old Kafka consumer, Flink Kafka consumer API is topic partition offset states, where the new one is source reader state. And the root cause of that RPC framework issue, that the huge size of inline metadata file, is that when you switch your application from old Kafka consumer to new Kafka source, you just simply keep the UID is the same UID. So this is actually the root cause of the akka frame size issue when the Flink job is trying to be restored from a save point file. So when the users migrating their job keep the same UID, the issue is that this will be the final save point file that they take with their new upgraded Kafka source API application. So the application will be having a state from the old Flink Kafka consumer, of course, the new source API Kafka source, and then they're just a value state, like keyed state. So when they reuse the same UID, this state data from Flink Kafka consumer becomes obsolete to our application, because our application is normally using the new source reader state objects for the Kafka source API. And then the situation is that since we are using the same UID, Flink just keeps the state data based on that UID. And then that UID is still being used by another operator, our Flink application. So this old, deprecated, or obsolete state data could not be removed from the Flink. And every save point, checkpoint, which is when our application starts to work with that new source API, for every checkpoint is just keeping populated this old operator state again and again into our save point file. So say our save point file is the size of our save point file, especially that underscore metadata inline state file, is going bigger and bigger for every checkpoint. So users are seeing their save point files are having an increased size, and then they could not understand, because their keyed state is same, their distinct key count is same, why the state is going bigger and bigger, because it is still using the same operator UID, and then Flink doesn't know what to do with this old state, since it's still seeing the objects with the same UID with this Kafka source operator. You can see with this save point file, the state data for those topics partitions is just updating itself again and again. Normally we should be seeing only like 10 lines of data here, but every checkpoint, since it's using the same UID, it's copying itself again and again. You can see we are now on the line 1000, so it's just keep copying. And when we just see that underscore metadata file with some hexadecimal editor, we can see the objects uh, like topic partition offset states are still being seen in this save point file. Also, some users, when they just recover their state from that save point file, they can see in their job managers if their memory is low. They can even get some out of memory issues with their job managers when they try to fetch that huge sized underscore metadata save point file. So the solution simply, we shouldn't use the same UID for our upgraded Kafka source operator. We need to set the UID to a new one. So instead of using the same Kafka source UID, you'll need to set a new UID for our operator. So the name is Kafka underscore like source underscore new. And then we also start our Flink job by allowing non-restored state. So whenever our Flink job starts, since the UID is changed, it cannot use the old operator's state again. So it needs to, remove those state information from its metadata file. Then it will be just starting to store states for its Kafka source, new Kafka source operator. But it cannot simply be done without using this old operator state, because we need those, partition values to start our application from. Otherwise, we shouldn't, start our Flink application, start from the initial offset of the Kafka topic. So how we just fix that issue, instead of relying the Flink Kafka consumers stored offsets in the save point file, we just simply set our old application has this group ID, and then set commit offset on checkpoint. So our old deprecated Flink Kafka consumer application is committing its offset to the Kafka. And then when we just switch to the new Kafka source operator, after finish migrating, we will simply use the same group ID. And then this group ID is having us reading, starting the offsets from committed offsets from Kafka. So instead of depending on a metadata file of our save point, we just depend on the committed offsets in the Kafka. And you can see we just changed the UID to a new UID. So changing, like having a new UID, makes Flink to not use any of the operator states from old deprecated Flink Kafka consumer API. Then we will be starting our application from a fresh operator state. So what you need to do is step by step is do not upgrade your Flink version and then the Kafka connector version at the same time. And then make sure your Kafka consumer has group ID set, because we will be using this group ID to, initialize our new application from those committed offsets. And then the third one is set committed offset on checkpoint true for the consumer for old application, in order to make sure we are committing our latest offsets in Kafka. And then changing the UID to the new connector. So you can see that we just set the new UID for our new application, new upgraded Kafka source operator. And finally, we are starting our new job with allow non-restored state. So the Flink will not be using the stored state for the old Kafka operator. You can see these Flink Jira tickets related with that issue, because that issue is not specific for the Kafka operator. This could be any of the operator that you just use, that you just migrate, and then its object type is changed, and yet it's still storing some operator state in Flink. So you need to make sure that always set a new UID for your upgraded, migrated operators. Flink is working on this flip. That flip is not still being fixed for Flink 2.0. Flink is trying to manage that kind of situation automatically without user intervention, but it's still ongoing. And then in this Flink doc link, you will definitely see these steps that I mentioned, which is also mentioned by the Flink document itself for those migration steps. Let's go for our second issue, which is distributing the load evenly among the task slots. The symptom of this issue is our application throughput is low, latency is high, the application is having some less resource utilization. Some of the operators can see back pressure, and of course, our Flink application is using high memory. It has task failures and job restarts. These are some Flink UI states that you can commonly see, like failed, canceling, restarting operators. And some of the operators show like red boxes, which is showing like 100 busy states. So you can see in this screenshots, we will be having like 4 subtasks, and then some of the subtasks are having much records than other. So the size, the record size that they processing is much higher than the other. So that means that this operator is working on like 100% business, but the other subtasks are not working that high amount. So that means that this operator definitely is highly utilized than the other subtasks. So this is not something that we want. We would like this load to be evenly distributed among the subtasks. So what could be some root causes? Before jumping back to the root causes, I would like to mention how a record in Flink is like keyed, and then based on that key, it's just distributed into the task slots. Simply, when we read a record, we just use the key selector to select a key for that record, because we will be definitely using some key by for the distribution. And then by using some mathematical formula and the murmur hash, we just hashing that key value and then defining a key group. And then this key group, that key will be assigned by using the formula including parallelism and max parallelism to the task slot. So the keyed event is not directly put into a task slot. There is an entity called key group in between keys and task slots for Flink to distribute that events to the task slots a little bit more evenly by using this hash code. So right now in an example, you will see an example of a hotkey. The key A is having the majority of the events, where the other events are not having that much event count. So when this situation happens, key A is a single key, which will be having a single hash value. So this keys, events definitely will be processed by a single key group, because this is a single key value. And then this key value will be correspond to the key group by using our hash formula. And then, of course, this key group will be having processed in that particular task slot. Actually, the key group count is calculated by the maximum parallelism, and then the task slot is being defined by our parallelism of our Flink job. So these kind of situations with the hotkeys, actually there are some other techniques that Flink apply, such as rebalancing, local global aggregations, or if you are using Flink SQL has its own way to distribute the load in this kind of situations, but this is not actually in the scope of our talk. What I would like to focus on is these kind of situations where we have a hotkey group. You can see like key A, B, C, D is just distributing the events evenly between each other. And yet we can still have some issues that key A and key B's hash values can correspond to the same key group. This can happen because our distinct key count is too less. We are not having like millions of keys. We are just having only 4 distinct keys. And then the hash value of the key A and key B can correspond to a same key group. And then that makes this single key group is a hot key group. And then, of course, again, you can see that task slot 2 is much more utilized than task slot 1, 3, and 4. So these kind of situations, we can have a solution of dealing with our max parallelism value. So as I just explained to you earlier, related with the formula of defining a key to be assigned to a key slot, this is being defined based on your max parallelism value. So in this example, you can see that key B and C is corresponding to a same key group. Of course, ultimately, these keys data is being processed by the same task slot, but we have parallelism tree. So you can see that one of the task slots is idle. So by just increasing the max parallelism value from 128 to 256, our Flink application is able to set like key C a different hash value, which just that key will be correspond to a new key slot, and then this key slot will corresponding to another task slot, the key group, and then the task slot. So you can see that our data is evenly distributed between the task slots. And then of course also you can use a technique to reduce the maximum parallelism. This will also change the keying formula. And then in our earlier assignment, we only utilize like 2 task slots, but by changing the max parallelism value, just only changing one single parameter, you can see that our keys now distributed to these task slots, and then those task slots are correspond to 4 different actually key groups, and then those key groups are correspond to 4 different task slots. So by just tweaking the max parallelism value, you can see that Flink is now able to distribute those keys, events to a different task slots. So the key takeaway from here is that if your key cardinality is high, for example, if you are key buying your data based on for example, customer value, and then if you have like a millions of distinct customers, then the key buy will definitely, that murmur hash will definitely put your events into a different key groups, and then those will definitely be, going back to the task slots. Like it can be distributed evenly. But if your key cardinality is low, like you are keying by your data based on, like, for example, the G20 countries, that means you only have like 20 distinct keys. So in this kind of situations, that hash value, when hashing that key ID, can end up into a same key group. And then that same key group, of course, ending up into the same task slot, making that particular task slot become like a hot task slot. So you can consider to keep your cardinality of your keys high, or if not, just deal with this max parallelism value to distribute your data evenly between the task slots. And then here there's another example that we are just keeping the max parallelism value very close to the parallelism value. So in this kind of situations, we will definitely end up, for example, one task slot is having 100% more records than each other, because all of the task slot will have one key group, just one task slot have two key groups. So having very close values between the max parallelism and the parallelism is not suggested. So the solution is, like, the best practice is having a max parallelism value like 5 times or maximum like 10 times of your parallelism. That will ensure that you will be distributing your data evenly to the key groups and then ultimately with your task slots. So in this example, you can see our parallelism is 127. So we will keep the max parallelism 1280. So this will give us 117 task slots will get like 10 key groups, and then 10 task slots will have 11 key groups. So you can see that between task slots, the distribution of the key groups is almost even. So that the important note here is that, also would like to mention, is that when you change the max parallelism, your save point become obsolete. So either you need to tweak your save point with state processor API, or you just start your application with a fresh state. And then the third issue is, avoiding performance issues with the Kryo fallback. Again, our symptoms of our application is, latency spikes, throughput is degraded in our Flink application, especially under the load situations, and then less records processed per a given time. Of course, this is a significant indication that our Flink application, throughput is less and the latency is high. So these are the list of, Flink's serialization hierarchy. When Flink is reading events from sources, it's just serializing those data based on its own serializer. So Flink has its built-in serializers, which is supporting especially the primitive types, which are, string, long, integer, boolean, all these primitive types supported by Flink. Arrays, composite types like tuples, case classes, all are already supported out of the box. Of course, the POJO type classes, which is having public no argument constructors. If there will be, private entities, they should definitely have getters and setters. These are the rules of POJO. This is all supported by Flink. Avro is supported by Flink, especially if you have some cases like you are having schema evolution, would like to have Avro typed events are supported directly by the Flink's serializers. Of course, thrift, protobuf, all these types are commonly used in, Kafka use cases. They're all supported by Flink. But all other types, if you are trying to use with the Flink serialization, it's just automatically falling back to the Kryo fallback serialization, deserialization, if you do not apply some common rules, which I will be explaining you right now. You can see the comparison between the serialization types and their performance. You can see, like, with the POJO, we have like over 800 serialization performance. But if our serialization falling back to the Kryo serialization, you can see that the values is like 4 times less than the POJO serialization. So this is really important that we need to catch our application if it's falling back to the Kryo serialization or not. So when you see in your Flink application these kind of logs, like it says like class cannot be used as a POJO type because not all fields are valid POJO fields. Or another one is that like field XX record, like item type, will be processed as a generic type because Flink doesn't know how to process a type named like item. It's not a primitive type in the language, Java language that we are using. And then you can see like logs like class dot is like missing a default constructor, so it cannot be used as a POJO type and must be processed as a generic type. These are all info type logs, so users can easily overcome these kind of log types, but they're just impacting their Flink applications throughput and latency too much. So this is really crucial to fetch these kind of occurrences and apply the necessary logic to keep our Flink applications performing at its best. So this is, you can see an object that we are reading from Kafka, and this object is an order record which has its primitive types, plus it has a list type which is just keep the order items within that object. So all these primitive types is being known by Flink serialization, but this list type is not. So with these kind of situations, the solution is that, for example, if not all these record types are needed for your application, but you only need some of them for your like next level, like mappings, filterings, and all these kinds of Flink app processing, you just keep only the rows, you just read only the values that you only need to process data with. So you can see that we will be only importing those objects from those attributes from our order record object, and then just ignore the others, which is making our object size smaller, and then which is making the data which is managed by Flink is a smaller. So it's just increasing the performance of the application. Plus, if you are reading data from Kafka and you are using some analytical workload, you can consider using Flux, because Flux is keeping the event data not like Kafka as a row based, but it's column based. So for analytical workload, it's just improving the performance of your application, boosting a performance of your application. So you can even consider using Flux as a event store storage for these kind of use cases. But we're just focusing right now on the serialization, and then we just focus on this type which is unknown by Flink. And if we do not apply some rules, Flink will just falling back to Kryo by like managing this list typed order item events. So in order not for Flink to fall back to Kryo, what we need to do is to annotate this list type with the type info, which will be used list info factory class. So what we need to do is to use that kind of annotation, and we are just defining this class in our Flink application. And then we will also define list info factory class, which will be look like this. So this class will be extending the type info factory interface. So this will be giving us an ability to let Flink knows the type of those list objects. So when the Flink application runs, Flink will that the object type of list is not unknown for Flink anymore. So that's why Flink will be able to use POJO serialization for this list type by annotating it with this list info factory class. So, in order to make sure that Flink is not falling back to Kryo, this is the checkpoint that we can follow. We need to make sure, in order to have a POJO serialization for our Flink application for POJO type, we need to make sure that the class that we defined as a POJO must be a public class. And then that class needs to have no argument constructor. This is, the rules of POJO, which is required for deserialization. And then all fields must have accessible, of course, they should be public fields, or if they couldn't be public, they should have getters and setters in order for Flink to apply its serialization logic them. Of course, collection should have concrete types, just the list type needs that annotation that I just mentioned. But if it's not, it should be kind of like an array list, linked list, which is a known types for the language itself. And then finally, use type info for these generic types annotations. For example, if you have list type, by using that annotation, your Flink application is starting to know that list type and know what to do with that kind of object information. And finally, if you think that you need to catch the times when your Flink application is falling back to Kryo serialization, you can simply use this configuration event.getConfig.disable generic types. So by using this configuration, you're just making sure that your Flink application is not falling back to Kryo to process the data, but simply is just failing when it's starting. So you can understand that your application cannot use the generic types and is just disabled. You can easily understand based on your Flink application failure, then go over this checklist and then make sure that your Flink application is using the proper serialization for high performance. So thank you all for listening my talk. That's all about my talk. And I would like to inform you related with the Flink Forward, which is coming in this October to Barcelona. You can use this QR code to get more information related to the Flink Forward. So all these real-time streaming, people, we are just, of course, waiting for you to, check the details of the Flink Forward and then also follow its page. And then I would like to listen your questions if there's any. Thank you so much.
Hi, Nasi. That was great. Thanks so much for spending the time, with us to present your talk. Yeah.
Sure. Thank you. Thank you.
Okay. All right. So we're ready to take a live question from the audience, and so far we received two. So I can read them out loud, and then you can elaborate. Yeah.
Sure.
Okay. Perfect. So the first question we got is, for ordering needed workloads, is there anything Flink can do to address this challenge?
Yeah, for ordering the events, Flink applies some logic. If you would like to order events based on like a key by situations, which I just explained during the presentation, of course, Flink is placing like the events based on their keys into the same key slot. So those events in that same key slot will definitely be directly ordered. Okay, but if you would like to order the events regardless of their key value, but for example, for their timestamps, then you may need to do some rebalancing. So you just distribute all those different task slots into just one task manager and then perform the ordering like using some kind of data structure like sorted lists or these kind of structures. Of course, this will be a little bit like performance consumption will be high if you have like too much events. But you can also apply some like windowing logics and everything to window those events and use watermarks to also handle their let's say timestamp based ordering. So this could be done.
Perfect. Awesome. Thank you. The last one is, can the paradigm dynamically adjust based on the workload?
Yes, sure, definitely. Flink has different modes that can be applied, in different environments. But of course, we are now talking about mostly the Kubernetes environment. So if the job is being applied with some, Flink reactive mode, and then, we will be having, if there will be some extra task managers that to split our workload, then Flink job will rescale itself based on the load calculated in its pipeline. But, we can also apply run our Flink jobs with the Kubernetes operator. And then Kubernetes operator has a built-in autoscaler functionality, which is like applying, I mean, it can actively seeing, a couple of metrics if you are running in your pipeline, the operators like 100% business, all these kinds of things. So it's just automatically applying its auto scaling itself and then scale up when your job needs based on, reading that metrics automatically. But of course, this can also be done like manually by using, stopping your jobs, taking a save point, and then scale your job whenever job needs. But I think that question will be mostly related with autoscaler by using the Kubernetes operator.
Perfect. Awesome. Great. All right. I think that wraps up this session. And I want to thank you again for spending the time with us, Nasi. And then thanks for joining. If there are no more questions, I'll see you guys in the closing remarks session. Yeah.
Thank you. Thank you so much.
All right. See you guys there. Bye.
Bye.